Okay, so as we stated, we were going to demonstrate various elements of the Memory Master game just to get you pointed in the right direction. And the first thing that we're going to build in this video is going to be the bounce engine, if you will. So Logan, let's go ahead and show them the end result, what it is that we're going for by the end of this video.
Okay, let me run this demo app. And we see that we have 8 objects, 8 round buttons that are moving around the screen, bouncing on the edges, and also bouncing off of each other.
Now, we're not using any sort of true physics calculations here for bounces, are we?
No, we're not even calculating a true circle, the true angles that you would need to calculate a circle's bounce. And sometimes you can pick up on it, sometimes you'll see the buttons hit at a weird angle, sometimes it doesn't quite look right, but for the most part, since the buttons are moving generally fast, it makes sense. You see the buttons collide and go off in some other direction, which registers as a bounce.
Exactly. So this is going to work perfect since, once again, the idea is to keep things nice and fast, and we don't really need to go super sophisticated because we're not looking for any sort of, well, very realistic simulation. We're looking for something just like this. Now, what's going on to make these guys bounce around?
Well, there's a very simple engine behind the scenes, a simple engine similar to Precision.
Okay.
Where we have an actor system set up, we have an actor list, and the main update method continuously updates those actors in a loop.
Okay. Now for the bouncing, they've done a bunch of bouncing in the XNA Xtreme class.
Well, we've done bouncing off of the walls.
Okay.
All of that we've done before, probably in multiple programs. But what we haven't done is had various actors bounce off of each other. So we're going to need to look at the code required to make two things look like they bounce off of each other when they collide.
Okay, since I know there's just a little bit of whiteboarding involved, let's go ahead and close this down. And we're going to get to some whiteboarding here in just a second because I kind of want to get the explanation of how the bounce is occurring first before we start coding this entire thing out. So let's take a quick look at what's happening with the actual collision, basically how we're doing velocity swapping and all that good stuff.
Okay. Well, all of that is happening inside of this button class. Now, of course, we'll be getting to all these classes when we code the entire program out, but we wanted to go ahead and point out exactly what we were doing for bounce code. Inside of this button class, I have a method called checkActorCollision, and that's method's job is to go through all of the actors in the scene. If they're buttons, check and see if they've collided with one another. If they have, then we need to send them off as though they had bounced.
Okay.
And there are two parts to this code. The first part is simply a few lines of code that make the two actors swap velocities. And the reason we had done this is all of the buttons are the same size, so for all we would know they are the same weight. Therefore, if a fast object hits a slow object of the same mass, then you should have what looks like momentum transfer. Now, the slow thing goes fast, the fast thing goes slow.
Right.
So what made a nicer looking bounce was to simply take the two velocities of the two actors and swap them. And that's what we're doing with these 3 lines of code. I'm storing a velocity A in a variable, so I can get back to it later, where I store the velocity for button A. Then I take button A's velocity and I set it to button B's velocity. So there's one swap, and then set button B's velocity to that stored velocity A. And now I have the velocities of the two objects completely swapped.
So if one was coming at a 45-degree angle down right, and the other one was coming at a 45-degree angle up left, and they collided with one another, and the top one was slow and the bottom one was fast, they would now turn around and go the opposite ways. 45 degrees up would be the upper left one, and the bottom one would now go in a downwards direction, the 45 degrees, but their speeds would swap, of course, because we just swapped velocities.
And that collision would look perfectly correct. What looks a little bit off is if those two buttons were colliding, but only the very edges of the buttons clipped.
Right.
Then it would look a little weird because they would go in completely opposite directions and not just a slight...
Like a ricochet off.
Yeah, exactly.
Okay, very good. Now, we do have a problem, which right now you're correcting for, and this is something that I want them to see.
Well, that's the following 3 lines of code. And this is what I'll term sprite ejection. But first, let's demonstrate why this is necessary. Let me comment out these lines of code, and if I rerun the program now, the problem isn't necessarily going to be apparent. We still have 8 objects, and they're still bouncing around, but it doesn't seem like those lines of code were doing anything. This looks like the exact same result.
Okay, so now what happens if we crank this up to a whole bunch of buttons that are bouncing around?
Let's say we had maybe 40 of these all bouncing around the screen instead of 8. Now look what's happened with quite a few of these. Some of the buttons have collided and are now overlapping each other, but continuing to move as one, not bouncing away from each other. And what's happening here is they've collided, overlapped, and much like with the wall collisions, whenever we have a wall collision, we take that thing and make sure we move it completely back on the screen so it can never get stuck in the wall and vibrate back and forth.
Exactly.
That's basically what's happened with a bunch of these buttons now. They'll collide with each other and not have enough velocity to free from each other, and therefore will stay stuck together.
Meaning that as they swap directions, they're still colliding. When they swap again, they're still colliding. They swap again,
Exactly.
and they get this vibrating look that we see.
Right, or like, well, a lot of these will just continuously move in the same direction because now they have similar directions at this point.
Right.
They're swapping direction back and forth, and it's basically the same thing.
Exactly. All right, so to fix that, now we're going to deal with this sprite ejection code. And we can take a quick look at it here, and you can just kind of talk about it first, and then let's go whiteboard.
First, let's demonstrate what it looks like with a lot of buttons, but having the sprite ejection code.
Yeah, very good.
Now we see that has in fact cleaned everything up. So even though we have a lot of buttons bouncing around the screen, nothing is interpenetrating.
Okay.
So let's take a look at exactly what this code is doing. And to do that, we're going to swap over to the whiteboard for a minute.
All right.
So what we've got here are two circles that we've drawn. And this is to simulate, or to give an example of two buttons that have just collided and they're overlapping. So you can see one circle overlaps the other. So let's say that this circle has a center point right about there. This circle has a center point here. Now what the sprite ejection code's goal is to take these two objects and move them far enough apart so that they're no longer colliding. And we want it to move them apart to basically the nearest location where they're not colliding. Basically take the direction that they're going through each other and slide them backwards until they're simply not colliding anymore. And the easiest way to do that is to find the direction that they're to, like if you were to draw a line, let me go ahead and do that. If we were to draw a line, a pretend straight line between the two, we'll say that what this line could represent is these two objects' vector positions subtracted from one another. If we take this object's vector subtracted from this one, we'll essentially have a vector pointing between the two with a length equal to the length of the distance here.
Okay.
So what we could do is that's the first thing that's useful to us. If we were to take that distance and convert it to a unit vector, we would have something that might look like the following. Just a unit or a vector with a length of 1 pointing in the same direction as the difference between these two.
Okay.
So if we take that, now we have a direction that we can move these. So this guy represents the direction that we want to move each of these so that they can be moved apart. The next thing we need to know is how far do we need to move them before they're not colliding. And depending on how we've done the collision check, we might already have that. Since a lot of the collision checks in the past have been a simple check on distance, and we look for that distance to be less than a certain value between the two radii. Well, if we actually store the result of that instead of simply performing it, we could use that value to figure out how much they've overlapped. That would be this value end to end right here. Well, let me...
there you go. I'll help you out there. So, in fact, I'll make it look a little bit nicer while you're talking.
Yeah, I've kind of got the whiteboard at a weird, funny sideways angle. So
yeah, you and me both. So
compensate for up is down, left is right.
So basically, we're looking at from there to there.
Right. Our distance check will return, or we can set up our distance check so it would return that distance. So we can tell that, okay, these two objects are overlapping by this much. So we know that we need to move the objects. Now, we don't want to move both of them by this amount, otherwise we'll have two circles that are completely too far from each other. We want two circles that are just edge to edge, like as though they were touching right there.
Right.
So what we could do is we could take this new distance now, divide it by half, and take this circle, move it by this much distance, this direction, and this circle, move it by this much distance in this direction, and then we'll have them moved just outside of one another so that the circles are edge to edge but not overlapping.
Right. And we have that direction, of course, because of that unit vector that you've got over there.
Right. Now that we can take the distance that we got and multiply that distance by this vector, and then we have
so you get the right distance since it's multiplying by 1, but the vector's giving us the right direction.
Right, so it's almost like we're breaking apart direction and distance, but then reusing both of them.
Exactly.
We want a direction, but the distance isn't the full vector between the two. We instead just want a unit vector multiplied by a known amount of distance that we got from the collision check.
Okay, very cool. So let's go and switch back over and take a peek at the code real quick.
All right, let's swap back to, and the code to do that was, again, just like we were saying with the collision check. What I had done here when we're getting the distance between the two buttons is I'm using that, and I'm actually doing something a little bit different. What I'm doing is taking, since I want to know how much they overlap, normally a distance check would return something like, let's say that both of these have a radius of, looking back at the main code, they have a radius of 16.
Mm-hmm.
So what we would be looking for is if the distance between the two is less than the radius times 2, so less than basically that they have collided.
Mm-hmm.
We can look at that instead by taking the radius, figuring out what the overall diameter should be, that the entire thing is 32 end to end, and subtracting the actual distance from that. What that'll do is make it so that if they've overlapped by 1, then we get an overlap stored in this value. So 1 or more, whatever it happens to be. So then a collision is described as a case where overlap is greater than 0. Because overlap is, of course, going to be negative if they aren't touching each other.
Right.
So we get an overlap value so that later when we need to do sprite ejection, we can get a direction that is the normalized value of A's position minus B's position. So there's a vector that would represent their two centers connected. But we take that and we normalize it, so now we would have a unit vector, and we store that in direction. And since we have a direction, we know how much they're overlapping. We can say button A and move it along direction and multiply direction by overlap divided by 2, since the overlap is going to be the full thing.
Exactly.
Or rather, the overlap is going to be the entire overlap. We want to move half the overlap for one button in one direction,
right,
half the overlap for the other button in the other direction.
Which really is exactly what you were showing back over here. I mean, here's our overlap right here. And so what we're going to do is just take that, divide that by 2, and then we can use that for moving with the unit vectors in our two directions to get what we need.
It's kind of like we distribute the overlap so that half of the overlap is applied to button A, half of the overlap is applied to button B. That's why we need the unit vector, though. So we have a unit vector, so an amount of movement that represents 1, but times overlap. So if overlap happened to be 4, they'll move 2 for button A, 2 for button B.
Okay. All right, so very cool. Now that is basically how these guys bounce. At this point, what we're going to do is build this entire thing, and Logan's just going to walk through it all and talk about the whole thing as it comes together.
Right, we've just got the hard part out of the way,
yeah.
the core of what we want to get at. But we are, of course, going to show how we can wrap all of this together into an actor-based, simple demo program.
Okay.
So what I'm going to do is switch over to a fresh, brand new version of Visual Studio, and we'll start a new Windows game. And I'm going to call this Memory Master Bounce, since this is the Memory Master game that we're trying to put together. So Memory Master Bounce. And let's see, to get started, let's set up that one texture. So I'm going to go to the project folder, add a new folder that we'll call textures, or rather textures plural. Now I have a texture in our working folder that I'm going to copy over to the project folder. So there's our Memory Master Bounce. Here's our newly created textures folder. We'll drop that in place and then make sure we load that into Visual Studio. So we'll add a new existing item under textures. We'll grab content pipeline files and add the button graphic. All right, the next thing we need to look at is setting up the actor, because the way we're going to set up this demo is to have actor be the general movable actor class and then do all of the collision stuff inside of a button class. So I'll go in and add a new folder. We'll make this classes. And to this we'll add 2 new classes. We'll add actor and we'll add button. And let's see, for both of these, we've got actor button, and should we go ahead maybe and set up some of the basic things inside of the game, things like a sprite batch and maybe a reference for the texture?
Absolutely.
So back in game 1 we could add something like a sprite batch, which we'll call sprite batch. And we'll add a texture 2D. And we'll call that, maybe button texture?
Mm-hmm. I'm going to go ahead and throw in the random as well.
Right, since we want to, if you notice when the game launches, all of the buttons are automatically positioned randomly.
Yeah. And in the past, we always just go ahead and dump the random in at the very beginning.
Now this random I'm going to reuse later in other classes, so I'm going to make it public for the game class so that any other class that knows about game can get back to it. As a matter of fact, I want to make it static so that no specific reference has to be held. Everything can look back at the game class itself and call upon random. So I'm going to make a public static random field called random.
Okay.
And let's see, we've already got our button texture. So let's go and move down to initialize, where we can create a few things. We'll create the sprite batch. So sprite batch is equal to a new sprite batch, where we'll feed it graphics.graphics device. Then we'll take that random and set that to a new random instance.
Okay.
And now let's move into load graphics content and load in our button texture. So I'll say button texture is equal to content.load for a texture 2D, and we'll take in a literal string of textures \button. And while we're messing around with the sprite batch, we could go down to draw and just make a call to sprite batch begin and end, because I'm sure when we get into the actual drawing loop we'll probably forget that. So we'll drop in a call to sprite batch.begin and sprite batch.end. And there may be one or two small things that I've left out up until here, but this gets some of the basic things: a sprite batch, a texture, and a random object.
Okay.
Let me build, just make sure no simple errors have been introduced.
Now you want to go ahead and start over at Actor?
Yeah,
let's start building this thing up.
Yeah, let's turn our attention to Actor now, and let's implement all of our base Actor functionality.
Okay.
I'm going to leave the using for collections.generic, but I'm going to take out text. We'll be using collections because Actor is where we're going to store the actor list. Now I do want to add two using statements. We need to have access to XNA.framework and XNA.framework.graphics. So I'll add using Microsoft.xna.framework and Microsoft.xna.framework.graphics. And for the namespace, I'm going to strip off the class's sub namespace. Now, inside of the actor class, let's start with some fields. Let's put down a position, velocity, and a color field, because I don't think we're going to use the color field in this demo. You saw how all the buttons were.
Yeah,
right?
But hint, obviously.
But if you go back to the XNA page on 3dbus.com, there's the demo graphic for it, and that has the 4 different colored buttons. So let's drop some of these in place. I'm going to have a protected vector2 for position, a protected vector2 for velocity, and a private color for color. Now, why is color private and not protected? Well, simply because I was using these in the button class and I didn't actually need color in those. In a full implementation, it may be very likely that you would need color to be protected. Mm-hmm. Of course, since we're going to give properties to these, it wouldn't be absolutely necessary.
Right.
And if you want to get even deeper into that, the reason I actually wanted these to be directly accessible inside a button instead of using a property is if we go to the button in the other. I'm going to cheat here real quick. I'm going to go over to the button in our finished one, looking ahead into the future, and see that I'm messing with the components of the velocity and position directly, and that becomes very convenient here when doing the wall collision.
Gotcha.
So having these protected means I don't have to go through the effort of setting the entire property. I can set the subcomponents of them. But anyway, with these will be the 3 fields for actors. So now let's put down some properties so we can get to position, velocity, and color from outside of actor. So I'm going to drop down a region called properties. And we'll add 3 properties: position, velocity, and color. First, a public property, public vector2 called position. And this should be a simple matter of get and set accessors. So we'll have a get accessor return this dot position field. The set accessor will set the position field equal to the given value. And the other properties should be similar enough that I'll just copy this one and paste it 3 times. And I'll probably forget to set the color one to a different type. But vector2 position, vector2 velocity, and we'll snag the velocity field. And color. Now that I've made a point of pointing it out, we'll set the type of the color property to color. We'll call it color, and we'll have it access the color field.
Cool.
All right, and now I can collapse the region, and we can move on to some functionality.
Okay.
As a matter of fact, we'll move on to a field that I had left out. We need our list of actors, which I'm going to define as a static list inside the actor class. So I'll have a public static field that is a list of type actor, which we'll call actors.
Okay.
All right, now on to functionality, which I would have gotten to anyway, because the first thing we have to look at is the static constructor, what actually creates that list. So we'll make a static constructor for actor, and that constructor's job is to create the actors list. So actors equals new list of actors.
Okay.
All right, next we can take a look at the public constructor. So public constructor for actor will have no parameters, and what we want to do here is to make sure that when this actor is created, it gets automatically added into the actors list. So actor.actors.add this, and we also want to set the color to white. And the reason we want to do this is if we leave color defined and let it get initialized by the field initializer or by its default initializer, we end up with a color where all components are black, and including the transparency, so we'll have invisible actors.
Okay. All right. So where do you want to go from here? Because now we've got kind of the base set up, if you will.
I want to put in move at least. We can come back. We'll put in move, and we'll skeleton the remaining two.
Okay.
And then we'll get back to implementing them as we need them.
Okay. Sounds good.
So the first of these three methods will be the move method. I want a method that can be called upon to move the actor. This is a little bit different than where past demonstrations had the actor automatically move themselves on update. But I do want to have a specific move method. So I'll have a public void method called move. Move is going to take in a vector2 called amount. So it's basically move this actor by given amount, which is done by saying this dot position plus equals amount. This makes a good general utility method for the actor so that if you want to move it by something other than velocity, it's very easy to call upon that.
Okay.
And then, let's see, we'll skeleton in a few methods, and I do want to have an update method that can be called, so we'll put that in as well.
Okay. So for skeleton in, want to go ahead, we'll just follow straight down our list, start off with the set position.
Okay. We'll have a public void method called set random position. And as the name might suggest, this will be called upon so that we can have the actor auto-position itself randomly.
Okay. Now a set random direction.
All right. Public void set random direction. Now, set random direction is going to take in a parameter. It's going to take in a speed. Since when calling this, I wanted to, I didn't care about what direction they moved in, but I do want to be able to set the speed when this is called.
Right.
Now, one last thing I want to drop in is, like I was saying, a virtual method for update, so that any descendant actor can implement update and have that get called automatically. So we're going to put in a public virtual void update, where we'll give access to a parameter of type gameTime called gameTime. And I'm just going to drop the brackets off to the right of it because there's no implementation or no code in the actor version of this method.
Okay.
So let me build, make sure that there's no errors, and everything looks like it has worked. So
I'm going to go ahead and start getting button skeletoned in.
Yeah, we'll drop the methods down for button. So if we move over to the button class, we're going to need a few things, and the first is a...
First we're going to get the using set up.
Yeah, that's not a bad idea. What I'll do for that, for time's sake, is let me jump back over to actor, and I'm going to steal this using. All we need is XNA.framework. And we're not going to use any collections, so I'll take out both system.collections.generic and system.text. We'll replace those with XNA.framework.
Okay, now we'll go ahead and make sure that button extends actor.
All right, button shall extend actor.
And we'll remove the dot classes in the namespace.
That would certainly be a good idea. And now inside of the button class, the first method is going to be an override to update. So we can drop that in place. Override. Void. I'll let it drop update in place. I'm going to remove the call to base.update though, since we know that the base doesn't actually do anything.
Right. Now our two main things in here is going to be checking for wall collision and check actor collision, see if we've collided with an actor.
Right. So I'm going to drop these in as private methods. So I'll have a private void check wall collision. And a private void check actor collision. Then with these skeletoned in, we can turn around and go to our update method and make a call to each of these from update. So on every update, we'll call check wall collision and check actor collision.
Okay, cool.
We'll build, make sure there's no errors, and then we can decide what we want to implement first. Maybe let's go back to the game, get most of the game's code set up, initial spawning, update loop, and draw loop.
Sure.
Since we should be able to see things now. But of course, everything will just fly off the screen with no collisions.
Sure.
Then we'll come back and implement methods as necessary.
Okay.
Matter of fact, we'll probably end up implementing some things in Actor as we need random positioning.
Okay.
Let me also drop down one more method that's going to be really useful inside of game itself, and that's the range method. Now, this method should be familiar from programs like Pong and Precision. So let's drop in a private static float range, where range is going to take in a float for min and a float for max. And
you might as well start coding right there.
Right, because again, this is going to be exactly like before. So for, I guess you could say, more in-depth explanation, you can check back on Pong and Precision. But this is simply going to return a random value between those two. So we have return cast to float random.next double times the difference between max and min plus min as our offset to get within range. And that's it for the range method.
Okay, go ahead and do a quick build just to make sure that everything's good. And
right,
it is.
And it is indeed.
Okay.
So let's see. Let's go down to, I guess we just follow these in order, beginning and initialize. Since we don't have any type of game logic in place, no place for like a begin game or a load game or anything, I'm going to have everything kicked off inside of initialize. So that means I'm going to set our, basically the spawning the array of buttons is going to happen inside of initialize. And since we know we want to have lots of these spawns so we can test collisions, I'll spawn them from within a for loop. So we could drop down a for loop, tab twice to bring up the template, and let's loop to 8, so that original 8 that we had shown in the demo. Now what we want to have happen in here is to spawn buttons. Now I'm going to hold a button reference, a local variable inside of this for loop, just so we can set up some properties on these newly created buttons. So we'll define a button variable and create a new button, store that in the variable, and then we'll turn around and set a few things. We'll tell that button to set a random position. So have it set somewhere randomly on the screen instead of 0, 0. Then we're going to come up with a speed for that button. Then we're going to call set random direction using that speed. So we'll drop in a float variable called speed, and we'll set that equal to a range value. Now for the range value, for min and max, we want some number, a fast number, and a slow number. But instead of hard coding things directly here, it would probably be a better idea to set a constant at the start of the app so that we can change this more quickly without having to jump around and code so much. So let me jump all the way back to the start of the game class, and we'll define a few constants.
Okay.
We'll make, since we're on the min and max, or well, more specifically the button, let's actually set up a few properties for the button itself. We'll set
start with num buttons, and we'll go ahead and replace that magic number in the loop as well.
That's a good idea. Let's make a...
just a reminder to everyone, this is, of course, just a proof of concept. So sometimes when you're doing quick proof of concepts, you are going to throw in magic numbers. So I just wanted to remind people that does happen from time to time. This isn't an actual prototype that's going to, the production line. This is just proving this is how it works.
Exactly. Like you said, this is a proof of concept. This isn't even like you would consider alpha stuff. This is just, we want a technical example of bouncing
You want to be able
objects.
to bring your director in, or whoever it may be, your supervisor, and say, all right, here's the bounce I've come up with. Does this motion look good? And then you can start going from there.
Because really the idea is that most of this stuff, this simple lightweight actor engine, wouldn't even necessarily be used in the final result.
That's right.
The two key elements of this entire program are those 6 lines of code inside a button where the buttons are bouncing off of each other.
Precisely.
All right, so let's set up some properties for the buttons. Let's begin with a number of buttons to have on the screen in this test. So I'll make a constant integer called button num, and we'll set that to 8, and then we'll use that to drive the loop.
Okay.
Now I also want to have, let's say, a setting for the button's radius, because that's going to be useful in the button class when it goes to do collisions. And that means I'm also going to make it public, so that I can get to it from the button class.
And of course, where do we get this? Well, the graphics 32 by 32. So
right, that's we aren't having this auto adapt to the graphic nice. But again, this being a test app means that we could just change this. So for now, we'll just leave it as a property, which is nice because we could see the effect of making the radius different than the graphic if we wanted to.
Right.
So we'll make a public constant called button radius. And we'll set that to 16 because, like you said, we're using a 32 by 32 graphic for the current button. Now let's also have two more constants. Let's store a max speed or a speed min and a speed max to drive the range when making new buttons, so that at random some of them can be faster and some of them can be slower.
Okay.
So we'll make a const float button min speed or button speed min. And let's set that to a value of 1. And I'll copy paste that line for brevity's sake. And we'll make a button speed max, which we'll set to 4. And let me change the casing on this button.
And go ahead and put an X on max.
And
I know you like those Macintosh computers, but move down 2. And for max.
Oh,
there
nice.
we go.
Wow, I was trying to figure out what that, because there's like some compiler there, well there still is, constant, let me build and figure out what this is. Button radius, public, const, type. What is this? It is an integer. Thank you, compiler. Okay, so a few properties set up for the button. I guess while we're defining constants, let me put in 2 more.
Okay.
Let's define the screen width and height, because that's going to be necessary for the wall collisions. I'm going to make 2 public constant integers for screen width and screen height. Screen width, we'll set a small screen since the buttons themselves are rather small. If we have 800 by 600, then we might have too much space in between them. And screen height, without a return key accidental press, would result in something like this. We'll set the height to 480 and space out that a little bit. Alright, I think that defines all of the parameters we need for this test program.
And right before we jump back down into initialize, let's go ahead in the public constructor for game 1. Let's go ahead and use that screen width and screen height real quick.
Right, because of course the default is going to be 800 by 600, which means these are inaccurate until we use them. So let's jump into the games constructor and set the graphics.preferred back buffer width to screen width, and the preferred back buffer height to screen height.
All right, and now back down to initialize, and we'll change that 8 over to button none.
And now for the speed, we have the desired constants.
Exactly.
We have button speed min for the minimum value in the range, and button speed max for the max value. Now that we have a random speed chosen, we can use that to set the direction for the given button. So we can say button.set random direction and feed it speed.
Okay.
And that should send that button off in that direction. Now we could go and,
Well,
I guess while we're in the game class, do you want to implement the actor and button stuff, or do you want to implement the rest of the game class?
Well, just kind of following the flow of this, I would think at this point, how about we go ahead and put the code in place for set random position and for set random direction, so that now when these guys are initialized, they're properly set up. Or is that a little bit too much?
Well, we could do that. Then we could draw them. Then do update for the moving, for the necessary movement.
Exactly.
Okay, so let's take a look at set random position and set random direction inside of the actor class.
Okay, so we'll go ahead and start out with position then.
All right, set random position. This is going to be a definition of a vector using a few randoms as ranges. So we can say this dot position equals a new vector2. Now we need to get some x and y values, and we're going to use the game one's random to get these values. So we want not game time, game one dot random dot next, and we'll specify a range for next. Now we want this position to be such that all these appear completely on screen. We don't want to spawn anything half off screen. So that means instead of having the random start at 0, let's have it start a little bit off of 0. Matter of fact, we'll have it start at a value for the radius. So it's moved radius pixels onto screen, so make sure we have the entire thing on screen.
Exactly.
So the lower bound is going to be game1 dot button radius. And the upper value is going to be whatever the other side of the screen is minus radius.
Right.
Or game1 dot screen width minus game1 dot button radius. And let's drop down a line, clean a little bit of this up. And of course, that's going to take care of X. So we could drop down, paste that line in place, maybe tab it over a little bit. And now we're setting the Y value for the position.
Okay.
So again, put it radius pixels on the screen from the top, and make sure that it's screen height minus radius for Y.
Okay, very cool.
So end off the parenthesis, terminate the statement, and that's really all there is to it.
Build and make sure everything's happy.
So build,
Good.
no errors, and now we can look at set random direction.
Okay.
Now set random direction is going to be, once again, similar to the Pong example, in that we're going to pick a value in radians, and then we're going to create a vector based on that value. So it's like we're going to have a rotation in radians, then apply that to a vector too. So we'll make a float called rotation, and we'll set that equal to the result of something casted to float, and that is going to be game1 dot random dot next double. Now we want to make sure that we have a full 360 degrees that these could travel in. Pi is going to give us 180 degrees. So we could say math helper dot pi. Well, I don't know if that's floating point. Math helper dot pi is going to be float, whereas math dot pi is going to be double. Make sure I'm correct on that. And of course, next double is going to be double. That entire thing cast to float. So of course, well, pi is going to be 180 degrees. If we multiply that by 2, so we have 2 pi, that should be a full 360 degrees or a full circle. So math.pi times 2 times next double, cast the result of this to float and store it in rotation. So now I have a random rotation which can be anywhere from 0 to 360 degrees, full circle. Now we'll take this and turn it into a vector 2. As a matter of fact, we'll store it directly in the velocity. So this dot velocity is equal to a new vector 2, where the x component of this velocity is going to be the sine of the rotation radians, and the y component is going to be the cosine of the rotation radians. So we'll do a cast to float from math.sine of rotation. And then we'll drop down to the next line and set up y. Again, cast to float of math.cosine of the rotation. Finish off the parentheses.
Yeah, we're going to have too many parentheses up one line. Yeah.
Oh, whoops. Oh, those parentheses were ending off the whole thing. Okay, so kill one parenthesis, keep all this set up so we have full x and y. And now, of course, what this is going to do, since the result of sine and cosine is going to result in probably a unit vector based on the way they're going to counter each other. So using that unit vector, we could multiply that by remember the speed parameter given by random direction. So we'll multiply by speed and get an actual full velocity. So we come up with a random direction. And, we need to make sure that speed is outside. That would have been fun to leave in. What I had done is I had dropped speed onto y, so y would pick up the speed and x would not. That would have probably been a really interesting result when everything was going up and down instead of full direction. But nonetheless, good catch. All right, and I think that.
All right, so now when we start creating buttons, we have random positions for everybody, and we have random directions. We're not drawing anybody to the screen yet.
Let me build really quick, make sure that there's no errors, and everything's looking good.
All right.
So, like you said, we aren't seeing anything. As a matter of fact, if we run, we are most certainly not seeing anything. So let's turn our attention to draw and get all these actors set up to draw. First, let me take the background color to black to match the demo app. Then after we do a sprite batch begin, all we need to do is to loop through all of the actors. And since I have no need of an index variable here, I'm just going to use a simple for each in order to access all of the actors inside the actors list. So we could say for each actor called actor in actor.actors list, do the following.
And also, it's just a proof of concept. And also, even if this was the real deal, we're dealing with a very small number of actors.
Right.
So there would be no problems with speed here.
So inside of this for each, the only thing we're doing is a call to spritebatch.draw for each actor. So we'll say spritebatch.draw. We're going to be using the button texture we defined in the game class. And I believe it's probably override 5, or it's override 6, or we're looking for texture. And the reason I'm going for override 6 is we need the origin to be set.
Okay.
So let's see. For the position, well, that's going to be the current actor's position property. Rectangle, we have no source rectangle, so I'm going to null that out. Color is going to be the given actor's color. Rotation is going to be 0. Origin is going to be a new vector2 where we use the radius to define an origin. So button radius for x, button radius for y. And now we have everything centered. So before, when we had drawn on the whiteboard, we drawn the positions at the center.
Right.
This is why we needed this overload of draw so that we actually could set the origin. And our sprite effects are going to be none, and our layer depth will be 0.
And I think, did one guy get left out? Back.
Layer depth, sprite effects.
Back one before.
Origin.
Or no, okay. I think you were using a different overload here.
And I could have been.
That's
that
good,
might have
though.
been scale.
Yeah.
Well, where is scale?
Right
oh,
there.
Whoops. Okay.
Yep, it is left out. No, I didn't see it.
All right, scale is going to be 1. So to bring back the parameters, we define origin and somehow accidentally skipped to sprite effects.
That's
so
what you got me here for.
There is a scale thrown in there.
All right.
So we should be able to build and run, and now see an array of buttons thrown out onto the screen, positioned
And
randomly.
if you close it, rerun again, and very nice.
Ooh, and look what's happened. Some of them are sticking through each other.
So in this particular case, even though we have only 8, if we don't implement that sprite ejection code, these two guys would end up with a vibrating situation.
More than likely, because they're going to be immediately colliding and stuck together.
Yeah, there's no way a pixel shift on either side is going to pull them out from one another.
Unless they were both moving incredibly fast.
Yeah, exactly. Okay, very cool. So, of course, nobody's moving around because we have no code in update.
Well, let's address that. Update is just above draw. Let's put in a loop that will update all of the actors, and then really pretty much just update and move.
Okay.
So I'm going to make a for loop, and I'm going to make a for. I'll type for with 2 R's, bring up the reverse for loop template. And the reason I'm doing this is even though nothing is getting destroyed, in Precision we found that it was very useful to loop backwards so that as things got destroyed, we didn't have to worry about maintaining the correct index within the list, the correct index variable. So we'll go backwards just to make things more simplistic. Now, of course, length is going to be represented by actor.actorsList.count. Now, for each of these, I'm going to grab and make a simple actor variable here called actor. And the reason I'm doing this is otherwise we have to refer to these individual actors as actor.actors sub I. So that way we don't have to use this over and over again when addressing individual actors. So we're going to take that actor, we're going to tell it to move by its velocity. And then we're going to tell the actor to update, and we're going to give it the given game time for this call to update.
Okay, very nice.
So now, since we have a call to set random direction and we have implemented set random direction, we should be able to run and see moving buttons.
Very nice.
And we do. They all go flying off the screen, which leaves the button class to implement so we can handle collisions.
Okay.
All right, let's take a look at check while collision inside of the button class. And this is going to be a simple four-way if statement to check left of screen, right of screen, top of screen, bottom of the screen,
right.
Maybe vice versa. But let's begin with the first check, which is the left side of the screen. And we'll check that by saying this, if this.position.x has gone less than 0, or excuse me, not less than 0 because we want to bounce off the edge of the radius of the button, not the center. So minus or is less than game1 dot button radius. Then we've collided with the left side of the screen, and we need to take this dot position dot x and set it equal to game1 dot button radius, so move it back on screen if it has gone off screen. And we need to reverse the velocity. So this dot velocity dot x times equals -1. And that should work for bouncing off the left side of the screen. Let's see. We'll do an...
All right, go ahead and just copy that whole section. And
also, yeah, we could.
And then just check see if x is greater than.
So otherwise, if it hasn't gone off the left, see if it's gone off the right of the screen. So greater than game1 dot screen width minus button radius.
Okay.
If it has, we need to snap it on screen. So set it to game1.screen with minus button radius and reverse the velocity. Then we could take both of these directions and apply them to y. So copy the entire block, paste it in, and do a check for position.y less than button radius. If so, set it to radius, reverse it, and then for the bottom of the screen, see if y has gone beyond screen height. And if it has, set it to screen height minus button radius. Setting y, that is. And then reversing y.
Cool.
So we should be able to build and check and see if we have wall bounces taking place. And we do. So one thing is left, and that is button-to-button collision and bouncing. So we need to implement check actor collision, which is going to need to begin with a loop for each actor needs to look at all of the other actors and see if it has collided. So we're going to start a for each loop. I'll do for each actor called actor in actors list. And inside of here, what we're going to do is the very first check is to see, make sure that inside this loop that we haven't found ourselves. Because, of course, this code being part of an instance method for the button, and the button being an actor, we want to make sure that we don't ever attempt to collide with ourselves. So that means if the given actor we found in the loop is equal to ourselves, then we don't want to have any of this take place. We want to skip ourselves and go on to something else. So we'll drop in a continue. So we simply skip this entire iteration of the loop. Now, if it wasn't us, let's see if the two actors that we're looking at are in fact buttons. The reason I'm doing this is just in case you were to extend this example and put other kinds of actors in, maybe some that shouldn't collide with buttons. And also what I'll do is I'll set up two convenient variables that'll make a lot of the other code, or the remaining code in this method, easier to read. What I'll do is I'll make two button variables, one called button A and one called button B. Button A is going to be equal to this, casted using as to a button. Because, of course, we're looking at things as though they were actors here when we're looping through all actors. So we're going to attempt to cast the button and store the result in button A. And we'll do the same thing in order to make a button B variable, this time using actor. So we cast the found actor as a button and store that in button B. Now we do want to make sure that we have in fact found two buttons to collide before we attempt to collide them. So I'll first do a check and make sure that if button A is equal to null or button B is equal to null, then one of the casts didn't work out. So we'll skip this iteration with a continue. Now if we've gotten this far, we found that we have two different buttons that we need to do a collision check on. So we want to do a collision check, but we want to make sure that as we do that check, if the two things happen to collide, we have that usable in an overlap value. So what I'll do is I'll define a float called overlap. We'll set that equal to game1 dot button radius times 2 minus the distance between the two buttons. So minus vector2 dot distance for button A, button A's position, and
button B's position.
And there we go. I was looking at both the field, the protected field, and the property. We'll go with the property in this case. And that should return how much they are overlapping. Now, if this overlap value is greater than 0, that means we have some amount of overlap, and therefore we would have a collision. Yeah. Exactly. So if overlap is greater than 0f, then we know that there is some overlap, and that means, among other things, that these have in fact collided. So if they've collided, they need to bounce off of each other and start going in the other direction. So let's set up a few lines of code that will swap the velocities of these two buttons. And we'll begin by storing a temporary variable that will hold the velocity for button A. We'll call this velocity A with V instead of a C.
Oh, come on, it wasn't that bad.
So velocity A is going to be equal to button A's velocity. And now we have, since that acts as kind of a buffer, because otherwise we'd set A to B and then B to B and
right.
make everything not work. So we're going to take button A, set its velocity to button B's velocity. Then we're going to take button B, we'll set its velocity to the stored velocity A.
And the variable. Good.
So now we should be able to build, run, and as buttons collide, they bounce off of each other. So everything looking really good with a few buttons on screen, but if we attempt to have lots of buttons on screen, if we go to the top of the game class and change the number of buttons to 40, then we have a lot of problems with buttons getting stuck, interpenetrated.
Okay.
So now we need to write the button or the sprite ejection code. That takes anything that's stuck through each other and make sure that we have everything to send them off on their new velocities. But now we need to do something that's almost similar to the wall collisions, where before we send it off on its new velocity, we make sure we first move it out of the wall. So here that means we need to make sure we first move the actors out of each other before they start moving. So I'm going to come up with first the direction to move the two actors along when moving them away from each other. So I'll define this as vector2 called direction, and we'll set that equal to the result of vector2.normalize, so we'll get a unit vector from button A's position minus button B's position. Now with that unit vector, we'll multiply it by half the overlap in one direction for A and for the other direction for B. So we'll take button A, we'll tell it to move by the amount of direction times overlap, and then overlap divided by 2, since we want to move half for A and half for B.
Right.
And so button B, move in the other direction, so negative direction times overlap divided by 2. Now if we rerun, we have 40 buttons and no buttons getting stuck through each other and then moving together.
Very nice.
And that is all for the coding portion of the demo. Again, just showing a proof of concept for how we can write a scenario, a list of actors that all interact on screen, bouncing off of one another, and also handling sprite ejection, so none of the actors get stuck through each other.
Okay, and with that, that is going to wrap up this video. Thanks a lot.